Okay, welcome guys to lecture 8. I hope you're doing well and you're keeping your social distance. And let's start. Well, we're still at the query processor. We looked in the last lecture at the logical plan builder. We talked about how the logical plan is built, the two techniques for query optimization, using heuristics and cost-based optimization. The output from the logical plan builder is the selected logical plan or relational algebra tree that is considered to be most efficient. What we're going to look at today is the physical plan builder, which is really what gets run. This is what gets executed, and consequently there are two parts to it. The first part is what is a physical plan, and the second part is how is the optimization done on the physical plan. Now, if you remember from last lecture, I didn't spend much about the topic of what's a logical plan, because a logical plan is a relational algebra tree. You've studied relational algebra trees in database 1. So for me, I kind of just told you the fact, okay, this is a relational algebra tree, and we moved on to optimizations. But now with physical plans, we'll actually have to talk a little bit about first physical plans and the different ways to construct them, and then we'll talk about optimizations in the next phase. Okay? So let's start first about discussing the physical plan itself. Okay? Now, to have a physical plan, you must have a relational algebra tree, the output from the logical plan builder. In the physical plan, what we can do also, like we've done in the relational algebra trees of the previous lecture, we can change it to be a more efficient one from an execution point of view, not from an estimation just point of view, but from an execution point of view. We would also include in the physical plan instructions about what index to use, if there is an index. I don't mean by what index to use, whether it's a B+3 or a hash-based index. I mean realizing that the programmer who designed the schema and developed or maintaining the database, or maybe the database administrator, not necessarily the programmer, has created an index. But the question is, should the database engine use the index or not? So this is actually something a little bit new to you, because what I'm telling you now is you could create an index like a B+3 on a column, and the database engine decides to ignore your index and just go and do a linear scan. And you might ask, like, okay, what's the benefit of an index then? Well, actually what's happening is that you've written a query that forces the database engine at one point to do a linear scan because of a certain feature in your SQL or in your statement specifically. So instead of using B+3 and then doing a linear scan later on, it will just do linear scan. What this implies is to make benefit or to benefit from creating an index on a column, you don't just have to think carefully about the kind of index you create on this specific column, but you also have to consider the SQL statements that get executed against this column, and make sure that you don't kind of corner the database engine by forcing it to abandon the fact that you have created an index, and you force it because if you wrote that SQL so that it's going to use linear scan anyway, or it decides that it figures out from your SQL that it somehow requires to do a linear scan, not necessarily because of what you're doing to the column or what you're querying or the query that you've written on this specific column, but because of other parts of the SQL that queries other columns in the same table. And consequently, it decides, okay, since I'm going to do a linear scan anyway, I'm going to do linear scan and just ignore the index. So one of the things about physical plans is the database engine has to figure out is using an index an additional overhead, or it's actually it's an advantage. Okay. Now, interestingly, also, if you write bad SQL, the database engine always, and this is one of the reasons why actually database engines are so huge in size, they could decide, or a database engine could decide to build an index on the fly. Like, so you have a table, you filled it in with data, or a bunch of tables, and you fill them all with data, and you're writing SQL, and the database engine figures out those SQLs, are going to be faster if the database engine creates an index on the fly. Imagine, like, it will go and read the table and create several B+ trees on the fly just to answer your query, and after the query, it would just delete the index. Because doing linear scanning is too expensive, or it's just impossible because your memory is quite limited on the server you're running on. So it's just going to, try to run the query by just building an index. Okay, so all these things are decided upon in the physical plan. Okay. Now, at the lowest level, if you ask me, what's a physical plan? It's really two things. That's the most basic kind of physical plan if you're building a database engine from scratch that you will have to support. First of all, you must have relations, obviously, stored on disk. And you must have, and this is really the physical plan part, what we call operators, low-level operators, which act on these relations to produce some intermediate or final result. The figure usually to represent it is shown here in the slide, that I have relations stored as pages on disk, and the basic building block of physical plan is what we call an operator. This is historically the name that was given to it from early 1960s, and these operators will process the pages and produce some result. There's really nothing new here in terms of way of thinking, especially if you are into the Linux environment, because all the Linux and Unix variations of operating systems are kind of built using this notion of low-level functionality that you can invoke from the command line to do something. And really they are kind of related in an indirect way. It's kind of the same philosophy or thinking about doing something inside a computer, that instead of building something big, the approach is build something small and let it do one thing, on one thing only. And if you have many of these little small things, now you can make something that's much bigger. Okay? Now, the operators themselves are the relational algebra operators that you've learned in Database 1, plus other ones that we're going to see during this lecture. So it's not really deviating away a lot from what you would expect. I mean, what do you think an operator would be? It has to be implementing something related to SQL, because that's what you have written as a statement, that's what you want to support. Okay? So, but the point is, these are thought of as low level from the perspective of database engines, in the sense that if every operator will do one thing, but it's one thing that is related to database engines, not the general purpose operator in the programming kind of high level way of thinking. Okay? So let's look at the most basic, most actually popular operator. It's called the table scan operator or iterator. And not all operators are iterators, but we could classify operators as being either iterators or non-iterators. So the most basic ones of the two are, the table are the iterators. So an iterator is an operator that is very simple and very basic, because what it enables you to do is to iterate or visit every row in a table. Okay? So the first one we're going to look at, it's called the table scan iterator. And this is, as the name implies, it's just going to do reading of rows one by one from the first row to the last row, from the first row in the first page to the last row in the last page. Okay? Now, all iterators are implemented using what we call a design pattern. There are three methods: an open, a close, and a method that's usually called next or get next. Now, I know this will sound familiar because if you've used Java, especially during CS4, you should have seen iterators on array lists or on vectors or on other data structures in Java. And actually, the news I have to you is actually iterators in programming languages come historically from the database world, from database technologies. The first who used the notion of an iterator are database engines. Now, why? Because we always work with the following assumption, that the table is not going to fit in memory. And consequently, we divide it into pages. And once we've divided it into pages, we need a systematic way to traverse the content or go through all the content of a table from the first row in the first page to the last row in the last page. And the iterator is the solution. Okay? Now, a table scan iterator open method will use 2 pointers usually. I'm referring here as B and T. To point to, B points to the first block or page of the table, and T points to the first tuple or row in that block or page. Okay? So that's kind of the initialization. So you could think of the open here as being the init. And the close will release all resources. So it will remove any pages or blocks in memory. We'll just put them back on disk or just throw them away from memory. Okay? Now, here's the logic of get next. It says if T is beyond the last tuple in B in the current block, then increment B, which means go to the next block or page. If B is beyond the last block or page, then return no more data. Okay? Now, if B is not beyond the last block or page, then make T point to the first tuple in B. Okay? Now, inside this, I will use all T to store where T pointed to before. And I will increment T and then return the old T. The effect of this get next, it's working in a very, very kind of popular way in the programming world, that every time you call it, you get a new row. If you're using it against a data structure, not a database table, like for example, if you're using it with an array list, when you say get next, you get the next element in the array list. And internally, it has to adjust its local variables so that the next time you call get next, it gets you the next one. So if you have an array that has the values 1, 2, 3, 4, 5, you can just put get next in a loop to print or get access to the content 1, 2, 3, 4, 5. Okay? You don't actually have to create a variable in your method that you pass it to get next so that you specify the index of the next entry. It's maintained internally, as you see here in the logic. Okay? Let me go back here. If you reach to the last row in the first page, then you're going to go to the first row in the second page, and this keeps happening until you are out of pages and consequently return no more data. Okay? I know all of this at this point in your computer science education should sound very familiar. You have used this stuff before. Okay? Notice here number of things. First one is the name. It's called table scan. Sometimes you will find it in database engines called secscan, which is sequential scan. And this is indeed what's happening here. You are doing a sequential scan from the first row to the last row. Okay? Now, how many iterators we have? We have many iterators following the same logic. All of them will have an open, close, and get next. Let's look at this one, for example. This is doing a bag union iterator. If you remember from your database one, what's a bag union? A bag union will return everything in the two relations. Okay? It's not a set union which will not return to you duplicates. This just goes in from the first row in R to the last row in S. Okay? So I will open one of them and return all its rows, and when it's done, I will open the second one and return all its rows, and that will be R plus S. Okay? You see here in the code highlighted in red, I go, if the current relation equal to R, then get me a tuple from R using R.getNext. And this is something also you need to be aware of, that the reason why we like iterators in the database world, that they are nested inside each other. So here, a bag union iterator internally is using a table scan or a sec scan iterator for R to get the rows in R row by row. Once I am done with iterator. Okay. Now, this is the nice thing about iterators, that they are usable from within each other. Okay. Now, and in the close, obviously, I will close the two iterators I have opened: the sec-scan for R and the sec-scan for S. Okay. So the takeaway is that iterators are the basic building block of a physical plan. Table scan or sec scan and index scan are the most common ones. Obviously here you've seen sec scan, or if you've just seen table scan or sec scan, it's doing an O of n processing of the whole table from the first row to the last one. You could as well write an iterator that internally uses an index. In fact, in any typical database engine, for every index that is supported as a data structure, there will be an iterator. So there is a B+3 iterator, and a hash-based iterator, and a bitmap iterator, and it goes like this. Okay? For all indices you can imagine, there is always an iterator, because the physical plan building block is not incorporating directly the data structure, like, saying I'm going to create a B+3 and let's use a B+3. What it does is it's a tree that is built of iterators as the most basic way, or the most basic building unit or component in this kind of tree. Okay, so iterators are actually, for your information, exposed even at the programming language level. So I'm showing you here some sample code I got online, written in Java, that queries a table called coffees, okay, and to select, the coffee name and supplier ID and price and sales and total from whatever, okay. Querying some coffees table. If you look at the fifth line where it says result set rs equal to statement.execute query, from Java, I'm invoking the function inside the database engine to run this query that I have written in the string query. If you look at the next line, which is while rs.next, okay, this call rs.next goes from Java to the driver for the database engine, to the iterator code. The nice thing about iterators is that if you write a SQL statement that's so badly written that's actually going to retrieve the rows of a table that has 1 million rows, it's going to retrieve all of them, all of the 1 million rows, you don't force the database engine, or the programmer cannot force the database engine to read the 1 million rows one shot into memory. Because what you're doing is you're saying, I want the next row. This is rs.next. Next here is the iterator, get next call. So you read one row. And if you keep going on, yeah, sure, you will get the 1 million, but row by row. And the good thing about that, you're not going to force the database engine to load all the 1 million rows into memory one shot. Okay, at least not using this way. Okay, so they are heavily used, they are actually exposed in all high-level languages, whether you do it in Java or C# or Python. You have this notion that you have an object or a static method or whatever that you go .next, and it gives you one row. It's always giving you one row, or null in the case of Java if there is no more rows in the result set. Okay, so this is how this is how database engines manage the resources internally to avoid actually working with whole tables in one shot. Okay. Now, let's talk a bit about classifying operators. Okay, we have many types of operators, and they're not all the same. Some operators are way more expensive than others, and this has to do with the SQL logic It's not really a fault in the database engine implementation as much as it is related to the logic of different SQL functions that you could use in a SQL statement. Okay? So we will classify operators first by input type. Now, some operators takes tuple at a time to produce a result, and these are really nice. If you can always write SQL statements that you know will invoke tuple at a time operators, you're guaranteed to get acceptable performance. Okay? As I've written here, it says you can read only one page at a time and required work to only work with one tuple. Okay? What does that mean? Let me show you an example after this slide. Now, what else do we have before we go to the example? We have operators that require reading a whole table to give you any result. So if we go, compare it with the previous slide, we said we have an operator that will give you a result if you can pass it one row, or inside the logic of the database engine, if it gets one row, it will give you a result. And there are operators you'll have to give it a whole relation so that you can see a result. Okay? And then there is a third type of operators which require two relations so that you can see any result. Okay? Now obviously if you compare the three, common sense says that an operator that produces a result given one row is really nice. It's, that means I could load page by page, I could pass one row from this page I have loaded into the operator, and the operator will give me some result, and then I pass the next row and the operator will give me some result. So I'm happy, I'm always getting results as fast as I can ever get. But with full relation operators, I will have to load the whole table, page by page, pass the whole table, page by page to the operator, and when I reach to the last page, only then I will see some result. Now, for relation binary operators, it's even worse. I have to load two tables, pass all of the two tables to the operator to get any result. Okay? Now, this is one type of classification, which is by input type. Now, there is another type of classification, which is by algorithm type. We mean here by algorithm type how many times the operator passes on the data. So ideally, you want one-pass operators. Okay? What does one-pass operator means? It means it will pass on the data one time, from beginning to end. On the table, one time, from beginning to end. Okay? Now that sounds, I'm sure, for some of you, very scary, because what this means, we have something else. If I tell you we have as a classification one-pass operators, then do we have more than one pass? Yes, there are operators that will require multiple passes. So imagine now you have a table that has 1 million rows, and you want to do not one pass, but two passes. Okay? Or maybe even n passes. Now, the news actually to you is that all of these are actually implemented in a database engine. That's why when I started the course, I told you database engines are quite sophisticated and really huge in size, with millions of lines of code. If you try to Google, PostgreSQL, which is like the top open source database engine, to see how many lines of code it has, you will be surprised. It's in the millions and millions of lines of code, because everything we're describing here is implemented. Because depending on the schema and depending on the SQL we write, the database engine might be forced to use one of these guys we're describing. So it's not that the database engine will implement one and ignore the others. All of these guys I'm describing here are implemented as code in a database engine. Okay? So again, one-pass operators means you want to pass on the relation one time. Okay? Now I will show you an example of what I'm referring here in the rest of the slides with this business of fitting into memory. Okay? I will show you a detailed example here. Now, the one-pass operators are the important ones for us to study, because if we can put it in memory and we can do one pass on it, we are extremely happy, because we've achieved what we want with the least possible effort we can do, which is to do one pass. Okay, but if we actually run out of memory, we'll end up using multi-pass operators, which even are worse in performance because we will be putting the same page back and forth from this to memory, okay? This will become clearer as we go along. Now, the other alternative is what's called multi-pass operators, okay? And we use these guys, or the database engine would use these guys if the relation cannot fit in memory. So it keeps going back and forth on the relation, okay? I know that I'm giving you a little bit in this lecture of a long intro because I haven't shown you any examples yet, but the examples are coming. I want you to grasp the basic concepts first, that we have the basic building block is called operators, and they are classified by input type and by algorithm type, single pass or multi-pass, okay? Now, let's go back and see some examples. So I mentioned that by input type, we have tuple at a time, relation at a time, and binary relations, or two relations at a time. Let's look at tuple at a time. And these will always be, unary operators, which means they take one table. The examples we have, as you probably already guessed, the select and the project. Because when you type a select query, like select star from X, where A equal to 5, say, okay? You don't need to see more than a single row to decide whether you should include this row in your result set or not. So what this means, if you pass it a single tuple, a single row, you get something in the result set. Either you include it in the result set or you don't include it in the result set. Okay? Same thing obviously for projection. For projection, you will just grab the column or columns you're interested in and include it in the result set. Okay? If you're not doing any selection. So this is an example of what we call tuple at a time unary operator. Tuple at a time because it will produce a result when it sees one tuple. It doesn't need to see the whole table to produce a result. Okay? And it's called unary because it works on one table. Okay? Now, this is also, if you would like to think of the algorithm type, this is a one pass. So if I say select star from where X equal to 5, I don't need to load the table more than once. I just do it once. So consequently, it's a one pass algorithm. Okay? From the beginning till the end. Okay? Now, obviously, again, this is usually the ideal. If you would like to rank them, you want to work with one pass operators, or you want to actually be enabling the database engine. You want to write smart enough SQL to invoke inside the database engine a one pass tuple at a time operator. Okay? Now, are there situations where that's not going to happen? Of course. Depending on your SQL, depending on how smart the database engine, okay, depending on the stats available, and you will see that in your mini project 2, where I'm going to give you a number of SQL statements, and when you run them, you will see the plan, the physical plan that the database engine decides to execute to answer your query, and you will be surprised sometimes by the picks that the database engine make, okay? So, the nice thing about this is that this kind of operator, one pass, tuple at a time, fits perfectly with how we want to run things, okay? If the relation is too big, that we cannot fit it in memory, and we've divided already into pages, well, nice, I can read one page, put it in a buffer in memory, then run the operator, it will output the result in another buffer, and if the result set is too big, I can also page the result set and put it from memory to disk. So I could run a very, very, I can run a query on a very, very huge table with a very, very small amount of memory, okay? Because I really need 2 pages, one for input, one for output, even though the relation could be in gigabytes, and I don't have this in memory, I could still get it to work. I just need 1 page for input and 1 page for output, okay? Now, what about relation at a time unary operators? These are operators that cannot give you an answer unless they see the whole relation. Okay? A classical example is unique or even count. Okay? If you would like to count how many 20s you have in a column, the first 20 could be in the first row, and the last 20 could be in the last row in the table. So there is no way the operator will give you an answer until it sees the last row in the last page in this relation. And consequently, this operator is always slower than tuple at a time, because it's going to wait for the last row in the table to start giving you any result. Okay? Now, these guys could be done also one pass. However, you would always need, in addition to the operator, some kind of an auxiliary data structure, a secondary data structure that you use that fits the database way of working, so that you maintain the information you're collecting while executing this operator inside that data structure. Okay? For example, if you would like to count how many 20s exist in the table, so you're going to load the table page by page into a buffer. Okay? So this is nice. It fits into our way of working. But then every time I see a 20, I need somewhere to hold that I have seen a new 20. So by the end, I would like to report that I have seen, say, 70 20s. Okay? And this will be where I use the data structure holding the history as I've highlighted here. Okay? So it's still one pass. Fortunately, I cannot, I don't need to go back and count again, because I could, if I would like to count how many instances I have from every value, I could use the data structure to keep track of that. Okay? But the output buffer is not going to be filled with any data until I'm done with the whole table. Okay? But that should not be a big problem, because, yeah, of course, this is a little bit slower than tuple at a time. I will still have to run through the whole table before producing any output. But once I start producing the output and my output buffer is full, I can page it, put it on disk, so I can put the result set on disk, one after the other, to avoid filling in the memory. So this is an example of relation at a time unary operators. Okay. Now, the third type, if we classify them by input, are binary operators. Okay. Now, obviously, you should already be thinking of this. I mentioned it before. Join is a binary operator. Okay. Now, but this is not the only binary operator we have in the database world. Okay. Now the question is, can we fit it in memory or not? And if we don't fit it in memory, we will not be able to run it in one pass. We will run it in multi-pass, as I mentioned before. So all these guys, not just the join appears here as the last one. All these guys are actually binary operators. They require two tables. Okay, union, intersection, R minus S, S minus R, and a Cartesian product. All of them require two tables. Okay. Now, we have here really two scenarios when we come to implement this, and again, database engines will actually have the implementation for the two scenarios depending on which one it needs to use. It will use. Okay, so we have a scenario where both R and S do not fit in memory. So we have a big issue here. I cannot fit it. Okay, neither R nor S, the two relations I'm working with, will not. Either of them will not fit into memory. Okay. The other scenario is one of them will fit into memory. Now you might ask, okay, why are we coding for or talking about this second scenario, since the first scenario is the more general one? Well, because you see, if you remember from last lecture, we talked about the containment of values principle, which is related to the foreign primary key issue. Usually when you work with two tables, if they are related using a foreign primary key thing, then one of them will be small and the other one will be big. Okay, so usually when you relate tables, the more common version we see in the database world is that one is much smaller than another. Okay, but we still have the situation where both are too big and they cannot fit in memory. Okay, so let's talk about when one of them fits into memory. Okay, let's see implementation of an operator that will do R union S. Okay, and this is a set union, not a bag union like the one we've seen before. So I will always use S S, for small, so I remember S is the one that will fit in memory. Okay? Now what we're after here is an efficient way to do the operation of R union S. So this will be our efficient strategy. I will read all of S into memory, which is what the first point here says, okay? And make it accessible through an in-memory index structure. Why? Because in the union situation, I don't want to repeat the values. In the set union, like if, say, the number 10 appears in set R and the number 10 appears in set S, I want 110. I don't want to have 10 duplicated, okay, because this is a set union. So this is also an example, if you noticed, of building an index on the fly inside the operator, okay? So I will read S into memory, and I will create an index for S's content, okay? And then I will output all tuples of S while reading, because since this is a union, I need everything in S. Okay? Now what I'm going to do is to support the union functionality correctly. For each tuple that exists in R, I will search in S's index. If it exists, I'm not going to output it because I have already outputted it when I was outputting S. If it doesn't exist in S's index, I will output it. And this way I get R union S. Okay? So there is a number of new things here. The first one is that I'm building on the fly an in-memory index. Okay? You will see that in mini project 2 that database indices will do that a lot. Okay? It's on the fly and it gets deleted afterwards. Okay? Now, the second thing is it's implementing the basic relational algebra set union as an operator. As I mentioned, the operators, the basic kind of operators are what you've learned in database 1. All the SQL functionality, anything that you can write in SQL as part of a query has a corresponding operator implementation. Okay, so this is how it's typically done. Okay. Now there is another question here. You should always ask yourself: is this one pass or multi-pass? So let's trace through these steps. I said read S into memory, so this is one pass on S. And then while I'm reading it, that's why here I'm trying actually to avoid to make multipass. While I'm reading it to build an index, so this could be an index, could be a B+3. I'm reading S and inserting the entries in a B+3. I will output it, so I avoid reading it one more time. Okay, and then I will go to R and I will read all the tuples. So this is again one pass on R. Okay, and search if it exists in S's index. So I'm not going to go to S and read it again. So what this means, this is a single pass operator. It's doing one pass on R and one pass on S. Okay? Now, let's do set intersection. I think now we're getting the idea. So, again, I'll read S into memory and make it accessible through an in-memory index structure. Could be a B+3 or whatever. And then, for each tuple in R, I will search if it exists in S. And if it exists in S, I will output it. Okay, notice here, I am not outputting S. I will use S to build an index. Why am I using S? Because it's the smaller of the two. So I can fit it in memory and create the index on it. Why am I creating the index? Because I'm going to search and I want to speed up the search. So obviously here, since there is no range searches, the right choice here shouldn't be a B+3 actually. It should be a hash-based index. Hopefully that will fit in memory if S fits in memory. Okay? And then for each tuple in R, I will search if it exists in S. If it exists in S and I'm getting the value from R, so it exists in R and it exists in S, so it's in the intersection between the two, so I will output it, the tuple. Okay? Now what about set difference? I want everything in R that is not in S. Okay? That's what the set difference means. Again, S is the small one. I will read it into memory. I will create an index because I'm going to search, and then for each tuple in R, I will search if it exists in S, and if it exists in S, then I will ignore it. If it doesn't exist in S, because I'm getting it from R, and it doesn't exist in S, that means it's only in R. That's what set difference is about. R minus S means everything that's in R that is not in S, then I will actually output it. Okay? What about S minus R? Again, read S into memory, make it through accessible through an in-memory index, and then this is new a little bit. For each tuple in R, I will search if it already exists in S, and I will delete it from S if it exists. So what will remain in S are things that are only in S but not in R, which is exactly the meaning of S minus R, and I will output that. Okay? What about a cross product? Okay? This is what we're going to do. Again, read it into memory. Now, a cross product is a blind match, as we mentioned before, so I don't actually, not going to do any kind of search. So what I'm going to do is, for each tuple in R, I will combine it with S and output the result. Note that all these ones I have actually discussed are doing one pass. We haven't seen any multi-pass yet. Okay? Basically, I will read S into memory, and then since S will remain in memory, I will read R. R does not fit in memory, so I will read it page by page, get every row from there. I want you to tell me if this is, or try to think with me. You cannot really tell me here. I want you to think with me if this is multi-pass or single pass. Okay? S is read in one pass and put into memory. Okay? R is read page by page, and for every page we read from R, we're going to read row by row, and we get a row from R and match it with everything that exists in S. But where is S? S is in memory. Okay? So this is again a single pass, because when I say a pass, I mean reading from disk and put it in memory. So I have done that once for S. Okay? I will keep iterating on the rows of S in memory for every row in R. But I will never unload S from memory while I'm doing that. So it was one pass to read S, all of S from disk and put it into memory, and then I went into R from the first page to the last page, combining every row from R with all the rows in S. Okay? So both of them are single pass. Okay? Now, let's look at join. Okay? Now, obviously there has to be a common column, and in this case it's going to be the Y. Obviously here again there is some kind of a search involved, because when I grab a row from one of them and I get a value for Y, I have to go to the other one to find if this Y exists or not. So I will read again S and put it in memory, and I will create some kind of an index, either a B+3 or a hash table. Most likely it's going to be a hash table because I want to get an O of 1. And this again will be on the fly. And then for each tuple of R in each page of R, I will search in S to try to find it. If I find it, okay, and obviously if everything is working according to database rules, I should find it. When I find it, I will match the entry from R and the entry from S to create an entry in my result set. Okay? So this is again involving one pass to read all of S and one pass to read all of R. Okay, so the takeaway is relational algebra operations are called operators in the physical plan. Physical plan operators are classified according to how many rows or relations they act on, a row at a time, relation at a time, or binary relation at a time, and according to how many times they pass on the rows of the relation, single pass or multi-pass. Okay? Let's talk about the big topic of relation access. Now, when you're constructing, or when the database engine is constructing a physical plan, it has many options. And actually, everything I'm describing here is typically implemented in a database engine. Okay? If you look at the names down there, it says linear access methods, sorting-based methods, hash-based methods, and index-based methods. So a typical database engine would come with implementations for all of these guys, not just one of them. Okay? Obviously, the first one you're already doing in the project, it does not require much explanation. Linear access means from the first row to the last row, row by row, O of n processing. Okay? The new part here is really sorting-based methods. You haven't seen anything like this before here. And the last two should be very familiar to you. They are hash-based and index-based techniques. Okay? So let's start. Linear access methods. Simplest, obviously, you know, a linear access method involves nothing but using a sexcan operator. This is O of n, page by page, row by row. Okay? The thing is, sometimes you will find that it's very difficult to try to convince the database engine not to use a sexcan. And you will see that in your mini project too. Because if the database engine decides that the query that you've passed, and I'm mentioning this for the second time in today's lecture because it's a very important issue, if the query that you've written, if the SQL that you've written has any feature that will make the database engine decides that it's going to do a sexcan, then it does sexcan, okay? Even if you have an indices existing on the columns that you're working with, okay? So when I described before sexcan operators, I was referring to the general concept or the notion of linear scanning. But we will have linear scanning or linear access implemented for every imaginable or every SQL operator or function that you've learned in Database 1. So it's not just a sexcan. Sexcan is one version of it that does linear scanning from the first row to the last row. If you're doing in your SQL some kind of duplicate elimination by using the distinct keyword, there is a linear scanning implementation for duplicate elimination, which means go from the first row to the last row, eliminating duplicates. Okay? And then there is another linear access method for selection, which means go from the first row to the last row, looking at the rows and figuring out if this specific row I'm looking at matches my selection criteria, and if it is, included in my result set. And this goes on for all of them, for all SQL operators and functions you can think of. And another one for delete, another one for update, okay? And you should be already kind of experiencing this or writing similar code in your project, by now. That for every one of the basic methods we asked you for, like update, delete, insert, select, there's a linear version that goes from beginning to end. Okay, so that's why these are called linear access methods. It's not just one. It's not just sexcan, because usually sexcan means from the first row to the last row, just retrieving row by row. Okay, but on the top of sexcan, there are many other linear access methods built. You retrieve row by row and you decide to do something, like for example, update the row or delete the row or query the row to find a specific column value and so on. The essence of sort-based techniques is that there is a sorting activity involved. That's why it's called sort-based techniques. So whatever we're going to do, we have to sort. So I'm going to show you the logic behind this approach. This is a step that will always be done, which is sorting the data to be able to implement or perform a specific SQL function. Let's say you have a table that is sorted on column X, and you want to run or perform or execute a SQL function on column Y. Let's say you would like to count how many instances you have from every value. So if you have in the table 10, 10, 20, 20, you would like to count or find that there are 2 10s and 2 20s. So the sort-based logic will always start by sorting the data to be able to later on do the count. The thinking here again has to be database thinking, which means we're not going to be able to load all the table into memory to perform a typical sorting technique, like for example the one you learned in CS3, bubble sort or insertion sort or selection sort. So what we're going to do is we're going to sort copies of the pages of the table. So we create a copy of every page and we sort the data, according now to the new column. We said it was sorted on X, now I'm going to sort it on Y. But if you actually try to do that as an exercise on a piece of paper, you will notice that if you sort on Y, now every page is sorted, but not the whole copy is sorted. So let me try to highlight this using an example. So I have here one page, and I have here another page, and these two belong to the table. The table is sorted on X. And now I would like to sort on Y. So I'm going to make a copy of these guys. And I will sort on Y in this page, and I will also sort the content on Y in this page. But are these two pages together sorted? Obviously not, because when I was doing the sorting, I was doing local sorting. I only sorted the Y or the rows here according to this column value. So it was like, if it was like 5, 2, 1, I made it 1, 2, 5. But here also, I could see 1, 3, 9. Okay? So let me try to write them down. So now after the sorting, this is like this, 1, 2, 5. And this is like this, 3, say 6, 9. So this is sorted, but together they're not sorted. So in a sort-based approach, we make copy of the data, we sort every page separately, and then we go through a third phase where we do merging. So my final output actually should be like this. It should be 1, if this is my Y column, it should be 1, 2, 3, and here in my Y column, it should be 5, 6, 9. Okay? So let's count the number of passes we would do in such a technique. Now, I read this page and this page of table T, so that one pass. And then I created a copy in memory, and I sorted the copy in memory, and then I wrote it back to disk. And then I read again the copy from disk to do the merge step. That's why this is called two-pass algorithm. And all sort-based techniques are at least two-pass. Okay? With few exceptions here. But generally, you need to be able to sort and merge. So sort involves reading the initial pages, creating the new pages in memory, putting them on disk, and then loading them from disk to do the merge, and then putting them on disk, back on disk. Why am I putting back on disk and reading from disk? Because the assumption here again, database thinking, I will not be able to fit the whole table into memory, so I have to write the pages to disk to empty space in memory to load other pages. Okay? And this is generally what a sort pass technique does. For every SQL functionality, we will see, or there will be, we don't have time in the course to enumerate all and explain all of them, there is a sort-based technique for implementing a functionality, a specific SQL functionality. What I will show you is the duplicate elimination version, or a duplicate elimination sort-based implementation, if you would like. Okay? Now, what I'm going to do is I will skip the text and I will show to you using this example, and the text I just skipped is actually describing the steps here. So what I would like to do here, I would like to eliminate duplicates from my result set. So what I'm going to do is I will process the pages on disk to eliminate the duplicates. Now, What I have on disk are all these pages, 1, 2, 3, 4, 5, 6, 7, 8. Notice that they have already been sorted, so I've went already through the sorting process that I was describing a minute ago. And now these are the copies with the content of every one of those 9 pages already sorted. I would like to do duplicate elimination now, with the following restriction that I can only fit 3 pages in memory. And this will always be the case. The content of the table is much bigger than the memory. So I'm assuming here I just have 3 memory slots, just to show you how this is done. So what I'm going to do is I will load 3 of the pages from disk. I will put them in memory. And I will scan through them, outputting 1 of the values and ignoring the duplicates. This is how we eliminate duplicates. So my final output should be 1, 2, 3, 4, 5, and all the other duplicates are gone. Now, to be able to proceed in a systematic way, what I'm going to do is I need to keep, as part of this algorithm, some meta information about the content of every page, so that I load related pages. And that's what's going to happen. I will know from my meta information about the minimum and maximum value in every page to load related pages. So I happen to decide that I will load 1 and 2, 2 and 3, and 1 and 1 pages. The pages that contain those values, as you see here, now they have been placed in memory. Okay? So I'm starting from the smallest to the largest. I could run it as well from largest to smallest, it doesn't matter, but I have to either do it this way or that way. I cannot pick randomly any page, otherwise I will be stuck with pages in memory, and I would like to get rid of them to load new pages. So by working systematically from smallest to largest, or alternatively from largest to smallest, I will solve the problem. Now, so having queried the minimum and maximum, and I figured out, okay, I can load these guys, what I'm going to do is let's imagine there is actually a pointer that will take me or enable me to scan the content of a page. Okay? So I see a 1 in the first page that says 1 and 2 there. So I will output a 1 in my result set. And then I will go and look in the other pages. If there is a 1, I will skip it because I've already output a 1. What that means is the page that has been placed in memory in slot number 3, where it says 3 beside it. Okay, let me try to, just to make sure we're all on the same page here. Oh, we're all on the same topic. I'm referring to this guy. I will find that I've already outputted 1, so I'm just going to skip these guys. And since I have reached, again, this is a trivial example, since I have reached to the end of the page, I will load something else instead of this page. Okay? If there is any other page here that starts with a 1, I should have already loaded it. Okay? So now, I output the 1. Now, I'm not really deleting anything, but I'm showing you what I'm currently looking at here. So now I'm looking at the 2 in this page, and I'm looking at the 2 in this page, which is the original one that existed over here. And instead of the 1 that was gone, I loaded this guy. Okay, so now it's here, so I'm looking at this 2. If there was any other page that starts with a 1, that has a minimum 1, even if it was 1 and 7, I should have loaded it before moving beyond the 1, just to get rid of the 1 from my way. Now I'm working with 2s. So I would output 1 in my result set. Now I will output a 2 in my result set. And that will take me beyond this guy. It will take me here, and this is empty, right? This one is empty. It will take me here to the 3, and that will take me to the 3, which means I will empty this slot. So I would load this 2 and 2, okay? And then I will load this 2 and 5. And when I see the 5, I will stop when it's in memory, which will take me to the 3 later on. I will output the 3, and this will be gone. I'm labeling it, and then this will be gone, and I will keep doing the same logic. So this will be the picture. After I have outputted the 1, 2, and 3, I have the 5 remaining, and this 3, let me label it, and this 3 will be gone. And then I will load the 4, 4, I will output the 4, and I will load the 4, 5, I will skip the other 4, and then I will output the 5, and I will skip the other 2 5s. And this is, an example of, how important is sorting to this approach, because this will not work unless we have the data already sorted in every page. Notice that we didn't need to actually merge the pages, because not all sort-based implementations or variations require merging the pages together to produce a final sorted output. Here I'm doing only local sorting on the pages and then doing duplicate elimination.